Hello everyone, I am Dr. Karthika from Department of Biomedical Engineering, SNS College of Technology, Coimbatore. Today we are going to discuss about modeling in virtual reality. Modeling in virtual reality, we have three types. First one is geometric modeling, second one is kinematics modeling, and the third one is physical modeling. In this, we are going to discuss about kinematics, geometric and physical modeling. The main element of modeling is physical modeling. Here we have, in physical modeling, we have haptic interface control as a major thing. In haptic interface control, we have many components like collision detection, grasping, surface deformation, compliance and texture, hard contact, and physical constraints. These are mapped with haptic interface. Okay. Here we have haptics rendering pipeline. Here we have two stages. In stage 1 we have traversal, force, tactile and display. In stage 2 we have application, geometry, rasterizer and display. In the first stage we have collision detection, force calculation, force smoothing, force mapping and haptic texturing, and the traversal, force and tactile. In the stage 2 we have scene traversal in application, and in geometry we have view transform, lightning and projection. In rasterizer we have texturing, and finally we have virtual reality display. Okay, this is stage 1. First one, in this we are going to discuss about collision detection in virtual reality. Okay, to detect the collision, we use bounding box collision detection for fast response. Here we use two types of bounding boxes with fixed size or variable size depending upon the enclosed object orientation. But mostly we prefer bounding box in variable size because fixed size is computationally faster but less precise. See this one here, this diagram, it clearly shows the variable size bounding box and fixed size bounding box. Nowadays we prefer variable size bounding box for highest precision. Okay, see this one, in collision detection, here we consider object 1 and object 2, and here object 1 we have k1, i1 and j1 as the coordinates, and object 2 we have k2, i2 and j2 as the coordinates. Here to detect the collision, object 1 and object 2 coordinates are it should be in line with world coordinates. If not, the collision will be detected in the output side. Okay, suppose if any undetected collision are there, how do we calculate that kind of collisions? Here, see this diagram. Here the ball at time t is mentioned, and we also have ball at time t plus 1 bar fps. What do you mean by this fps? In virtual reality, we consider the scenes. To display the scenes, we are using modeling techniques. So here fps, it represents frame per second. Okay, suppose if any delay or if any undetected collision are there, we consider the longest distance from input side to output side. If the longest distance is d, means if d less than, we multiply it with 1 bar fps, then collision is undetected. Here v is the ball velocity along its trajectory. Okay, and also we have a two-stage collision detection, an approximate bounding box stage and followed by a slower exact collision detection stage. For more precise detection, we have two-stage collision detection. See this one. In this we have bounding box pruning, multibody pairs and simulation. Here pairwise exact collision detection is analyzed. If it is S, the collision response, and we have to simulate the bounding box. If it is no, then we have to simulate the bounding box, and if it is no, there is no collision. If S, some collision is detected. Okay, and for exact collision detection, we consider object A and object B. In this we use external Voronoi region and internal Voronoi region. Okay, suppose this object A and object B are not in line with this regions, collision is detected. If it is exactly matched with the regions, then there is no collision there. Okay, and in haptic rendering pipeline, the next stage is force calculation. Previously we have discussed about collision detection, and in force we have force calculation, force smoothing and force mapping. Okay, in this first we have to identify the haptic interface point. In this haptic interface point, we consider the object polygon, and the first haptic interface point is identified, and it should be in line with the haptic interface point at the final stage. It shows the penetration distance. Okay, here a force output for homogeneous elastic objects. Consider the elastic ball. In this we measure two saturations. One is hard object and second one is soft object. Hard object, the distance is d max 1, and soft object we taken as d max 2, and the distance is a penetration distance. And if we need to calculate F, means F equal to K multiplied with the D for 0 less than D less than or equal to D max, and F equal to F maximum when D max less than D. Here F max is that haptic interface maximum output force. Here remember one thing, small FPS means frame per second. If it is caps F, here we mentioned as force. Okay, next one we have force shading, and this force shading we consider non-shaded contact forces. First one, second one is real cylinder contact forces, and the third one is contact forces after shading. Also we have F smoothen formula, it is equal to K object multiplied with D multiplied with N bar for 0 less than or equal to D less than or equal to D max, and F smoothed equal to F max multiplied with N bar for D max less than D, where N bar is the direction of the contact force based on the vertex normal interpolation. Okay, next one is haptic mesh. Okay, here a single HAP is not sufficient to capture the geometry of fingertip object contact. For example, elastic ball. Okay, in this, the curvature of the fingertip and the object deformation, it need to be realistically modeled. Here, see this scene sequence for squeezing an elastic virtual ball. If we press the ball, it should give a real experience for the users. So we use haptic mesh. First point is mesh point I, and also we have penetration distance for mesh point I. For a better experience, for a better real world experience, we use haptic mesh. Okay, in this we have to calculate the haptic mesh force calculation. Here for each haptic interface point of mesh, F haptic mesh I, it is equal to K object multiplied with D mesh I, and it is multiplied with N bar surface. Here D mesh I are the interpenetrating distances at the mesh points, and N bar surface is the weighted surface normal of the contact polygon, because we consider the polygon as the input object. Okay, and also we have force mapping. See this diagram, how forces are mapped with the object. First one is haptic mesh, and also the F displayed and the F global, it should be in line with the haptic mesh. Then only it gives a real world experience while pressing the ball, real ball experience. Okay, next one is tactile mouse. Tactile patterns produced by the Logitech mouse. Here see this one, force time, based on the force and time. We have inline the haptic meshes for giving better experience in virtual reality environment. See this one, object polygon. We have three axes X, Y and Z. Here suppose we want to calculate the force of the texture. F texture, it is equal to A sine of mx and sine of ny, where A, M and are constants. Here A gives magnitude of the vibrations and M and N modulate the frequency of the vibrations in the x and y directions. Because the object polygon, it has three axes x, y and z. See this one in behavior modeling. The simulation level of autonomy LOA as a function of its components. Here see this one. Here we have simulation components. It can be either guided lowest or programmed intermediate and autonomous high. First interactive object, we have autonomous, programmed and guided, and also we have intelligent agent and we have group of agents. For simulation LOA level of autonomy, the formula is f of LOA objects comma LOA agents and LOA groups. For simulation LOA, we have to consider interactive objects, intelligent agent as well as the group of agents. Simply it is called as groups. Okay, interactive objects, see this one. Interactive objects are needed for large virtual environments where it is impossible for the user to provide all the required environments, so we go with interactive objects. See this one, system clock, and also we have automatic door reflex behavior here. And also we have agent behavior, a behavior model composed of perception, emotions, behavior and actions. Here perception through virtual sensors makes the agent aware of his surroundings. For easy understanding, for better understanding, imagine virtual reality games. It gives better view about modeling in virtual reality. Okay, next one is object behavior. In object behavior, we consider autonomous virtual human and user controlled hand avatar. Next one is agent behavior avatars. These avatars are based on the user's wish, we can make it. User controlled hand avatar and autonomous virtual human. And we have emotional behaviors, a subjective strong feeling, anger or fear following perception. Two different agents can have different emotions to the same perception, thus they can have different actions. In virtual world, first we have to consider actions, behaviors, emotions and perceptions for each and every element. Based on the applications, we consider either behavior or only actions or emotions or perceptions. Depending upon the applications, we consider all the things. Okay, next one is how do we manage these models? What's the need for model management in virtual reality? It is necessary to maintain interactivity and constant frame rates when rendering complex models. Here we have level of detail segmentation, cell segmentation, offline computations, lightning and bump mapping at rendering stage and portals for effective model management. See this one. This is a perfect example for model management. Here only the current universe needs to be rendered. Current universe means the universe which we developed in the virtual reality environment. See this one. First one, we have viewpoint, object, light, adding objects to the simulation. We can add objects, also we can removing objects from simulation. Here entities ignored by the simulation manager, also entities considered by the simulation manager. Also we have limit of universe and limit of applications. For example, in Ludo we will have our own choices. No, we can play with the 2 players, 4 players, either it will be in online or offline. Like that in virtual reality gaming, the limit and the ignored entities and the entities considered by the simulation manager are based on the user's preference we can have. Thank you.